So now we're going to talk about interference of two sources from waves of two sources in two dimensions. And this also applies to three-dimensional spherical waves. So in two dimensions, you could imagine having two things on the surface of a pond vibrating up and down, and each little thing, each little source sends out these ripples of water waves, and the ripples of water waves from the two sources overlap and combine and form a pattern of some sort, depending on how the waves overlap at various points. So we'll first look at a single source and how we can kind of model that. If we have just one little source, this little green dot, giving off circular waves, and again this could be circular waves on the surface of a pond, so two-dimensional waves, or it could be spherical waves, so it could be like a little speaker, that's a small sphere that's vibrating, kind of pulsating in and out, and as it pulsates outward, it gives off like a maximum of compression, and when it comes back in, it in a sense gives off a minimum of compression, and it does this over and over and over again. So we can play this, and we can see these little, make it a little bit bigger, we can see these little spheres, or circles, whichever way you want to think about it, coming up, or coming out from the source, propagating outward, like ripples on a pond. So each of these wavefronts really represents a maximum of the displacement of the medium. And if you're standing at one particular point where their arrow is there, you can imagine the medium goes from maximum, minimum, maximum, minimum, maximum, minimum, and it just vibrates back and forth with a single source. And these waves are propagating outward in the radial direction. So we talked about before how we could describe these, if this is like a sinusoidal pattern of oscillation, we can describe it just like we did in the one-dimensional case with a sine function, and instead of having x inside of it, we'd have an r inside of it, and we'll look at that a little bit later. With this little animation, we can also change the wavelength. And I've got this set up so that the waves have the same speed, and if you change the wavelength, for example, make them bigger, the waves fronts are more spread out, they're traveling at the same speed as before, but now there's a greater distance between the wavefronts. If we make the wavelength smaller, then there's a smaller distance between the wavefronts, but they're still traveling at the same speed outward. The frequency is different though. If you think about being at one single point in space, the amount of time between maximums is now smaller, so the frequency is higher than when the waves are large. When the wavelength is larger, the amount of time between successive maximums is longer, so the frequency is lower. So you can play with this. This will be available on the D2L site for you to play with if you wish. So we'll pause that. And then we want to think about what happens if we add a second source. So we'll put another source a certain distance down below the first source and look at what happens when those two waves overlap. So we'll make this a little bit bigger. Scroll down a little. In this case, we again have time that we'll play. We have a green source and a blue source, just colored this way, just to distinguish one from the other. The green source is going to give off circular wavefronts that'll look, well, we'll color them green, just so we can distinguish them from the blue. The blue source will have blue wavefronts. And then we can change the distance between the sources with this little slider. And we can also change the phase constant difference between the sources. Delta Phi 01 minus delta Phi 02. We can change that. And just kind of think about how that affects the pattern. So right now, the phase difference is 0. What this means is that these two sources are in phase with each other. When the green guy is giving off a maximum, the blue guy is giving off a maximum. When the green guy is giving off a minimum, the blue guy is giving off a minimum. So let's see what that looks like. And right now the distance is set up to be a 1, meaning 1 in terms of the wavelength. So they're a distance of 1 wavelength apart. So if we play this, you can see the wavefronts propagating outward, and the green ones and the blue ones are overlapping. And we'll pause here in a second. Let the screen fill up a little bit. So we'll pause. And you can see that these guys are 1 wavelength apart. So in this direction right here, you can see that the wavefronts are overlapping, maximum on top of maximum. So this would be a region where along this line you would feel, if you were sitting there, you would feel these waves going by. We'll just continue to let this play. You would see these waves going by, and you'd have a big maximum and a lower minimum. You'd have large variation, large vibration in the medium. If you look over here, also in this direction, you also have maximum overlapping with maximum along these points, and minimum overlapping with minimum, all along this line here. And then if you look, let's pause it, it's a little bit easier to see when it's paused. if you look in this direction, roughly about like this, you've got minimum overlapping with maximum. For example, right there, right there, right there. The blue wavefront is right between the green wavefronts. So that's a maximum of the blue overlapping with a minimum of the green. And remember, minimum means not zero, but minimum means below equilibrium. So you've got the maximum of the blue representing above equilibrium combining with the minimum of the green representing below equilibrium. The resultant displacement is simply equilibrium. So all along the line in here, we would have a region of space where there is no wave. The wave is canceled out. It would be called a nodal line in this direction. These lines here, where we see that the maximums overlap with each other, that would be an antinodal line. You would feel large waves, large vibration of the medium in these directions. So what happens if we change the distance between these sources, make the distance a little bit bigger? We'll bring the time back to where we started, bring the distance up a little bit to say, let's just say roughly four wavelengths apart, right there. So now the sources are 4 wavelengths apart. We'll play that, let these waves come out, and again the phase difference is 0. So the two sources are vibrating in phase with each other. So let's play that and see what this looks like as they overlap, and then we'll pause it. But you can start to see a pattern developing as more and more waves start combining together. Again, in this upward direction, both above and below the sources, you see maximums on top of maximums lining up perfectly. But then you also see another pattern here. Maximums on top of maximums in this direction. And you also see maximums on top of maximums in this direction. And you see maximums on top of maximums again in this direction. Let's pause it. It's a little bit easier to see when they're paused. Okay. So this would be an antinode right there along this direction and down here along this direction. We'd have another antinode where maximums overlap with maximums in this direction. And then we would have another antinode here, like this. And then we'd have another antinode here, like this, coming up at an angle like that. And then finally we'd have another antinode like this. And then we'd have the repeat of that. Oops, scroll back up. We'd have the repeat of that down in this region as well. So counting, we have 1 up there. We have 2 up there. We have 3. Let's count that again. 1, 2, and then 3, and then 4, and then 5 down through here. So there's 5 antinodes, including this one in the middle. It turns out that for any point along this line in the middle, the distance between that point and one source is the same as the distance between that same point and the other source. The delta R, the difference in positions, is 0 along these points. Turns out along these points here, the difference in positions is 1 wavelength. Along these points here, the difference in position is 2 wavelengths. Along this point here, the difference in position is 3 wavelengths. And along these points up here, the difference in position is 4 wavelengths. So we'll see that again in a later figure, that there's a relationship between the number of these antinodal lines and the difference in position being a multiple of the wavelength when the sources are a multiple of a wavelength apart. So let's add a little bit more. Let's make the distance a little bit bigger again between these guys, make it a little bit more interesting, and then we'll change the phase and just see what that does. So here's 6. We didn't have a lot of time go by. We have enough waves on here, so the program just repositioned these sources. So you can see there's more antinodes. There's an antinode here, there's an antinode here, and you can go through and count them. All right, there's one right down the middle too. What happens now if I change the phase? What if I make these two sources completely out of phase? I'll click a pi here. That pi means that they'll be completely out of phase, meaning that when this guy up here, the green guy, is giving off a maximum, the blue guy is giving off a minimum. And watch carefully. This is an antinode right now. They're in phase with each other. When I click this pi, let's see what happens to that antinode. Take a moment and guess. Pause the video and see if you can guess what's going to happen before I hit the pause or hit the pi symbol. Okay, you made a guess? All right, let's see. Were you right? What does this become now? It was an antinode, but now along this direction, you see that the maximums of the blue are lining up with the minimums of the green and vice versa. So this is now a node. This is now a nodal position, a region where if you stood here, the waves would cancel each other out completely. And so everything's kind of reverse positions. Not everything, but some of these things have reverse positions. Again, along this line here, it's hard to kind of see, but you've got another antinode in this direction because you've got maximums overlapping with maximums. But certainly in this direction, we've gone from having an antinode when they were in phase to having a node when they're out of phase. So we want to look a little bit more mathematically at this and how we can predict what positions in space out here or over here or wherever we are is going to give you an antinode or a node or somewhere in between in terms of the total combined wave from these two sources. So mathematically, if we think about the fact that the waves from a single source, circular waves from a single source, can be written exactly the same as you wrote the waves for a one-dimensional wave in terms of a sine function, thinking about sinusoidal waves. The difference now, instead of an x, there's an r, because the distance is a radial distance, not just a distance along the x-axis. There's a minus omega t because the waves are moving outward in the r direction. There's a phase constant for the wave. And there's an amplitude for the wave. And the amplitude depends on the radius, technically. The amplitude depends on how far away you are. For now, that's not going to be too important for us because as long as we're looking at situations where the sources are close together compared to the distance that we are from the sources, any difference in amplitude from one source compared to the other is going to be negligible. If we have two sources that are, let's say, a meter apart, and we are maybe 1 or 2 centimeters from one of the sources, then yeah, you're going to see a significant difference in the amplitude from one source versus the other. So this amplitude won't necessarily be the same for each one. But we're going to look at not really an approximation, but just a situation where we are at a larger distance. Let's say we're a meter or two away from the sources, and the sources are just a few centimeters apart. In that case, we're pretty much the same distance from each source. Not exactly the same, but close. And the amplitudes, therefore, are pretty close to being exactly the same. So for simplicity reasons, we'll just assume that they are the same. So the displacement from source number 1 can be written like this, with a amplitude there that's just a number, call it little a sine of k times r1. And r1 is the distance from source 1 to the point that we're interested in. Minus omega t plus some phase constant for source 1. And then we have the other source has a equation very similar to that. We're assuming we have the same amplitude, and we have the same k, meaning the same wavelength wave, same omega, same frequency. Time is the same because we're just going to let time tick for everybody the same way. Nobody's going to be measuring time differently. But the position is different. So at a particular point in space, we're at a different distance from source 2 than we are from source 1. And then source 2 could have a different phase constant. And it's the difference in these two phase constants that leads to that difference in the phase of the sources that we adjusted in the last animation. That delta Phi0 that we'll look at again, that we saw. We saw this before in one-dimensional interference. So what we do then is we add these two things together. We add these two waves together to get the total resultant wave. And we use a trig identity just like we did before for one-dimensional interference. And come up with this thing that has this big thing in square brackets, cosine thing in square brackets, and then we have the sine function here, multiplying that. The sine function is simply just a traveling wave, sine of k times the distance minus omega t plus some angle. That's just the equation for a sinusoidal traveling wave. All this tells you is that at any given point in space, you're going to see, you're going to feel, you're going to measure a traveling wave traveling outward in the r direction. But this traveling wave has a certain amplitude. This amplitude depends on some things. This amplitude is the 2a cosine of all this stuff in here. And all this stuff in the curly brackets is what we had referred to before as delta phi. Delta phi is here. So this r2 minus r1 is delta r, the difference in distance between the source and the point versus the other source and the point. And the delta Phi0 is this difference in phase constants. So this delta Phi0 is what we call the phase difference between the sources. Are they out of phase with each other, in phase with each other, or somewhere in between? If they're in phase with each other, then this is 0. If they're out of phase with each other, then this is pi. Or we could really say if they're completely out of phase with each other, then this is pi. And anywhere between 0 and pi is somewhere in between. And then delta r is important. What is the difference in distance between the point in space and the two sources? Those two things combined give you this phase difference. It's the phase difference of the two waves that are adding together at that point in space. So we can combine this delta phi into the cosine function up here and just have a nice compact equation for that amplitude. 2a cosine of delta phi over 2. So we talked about this previously with one-dimensional interference, so hopefully this is familiar. So remember that what we want to do then is think about different points in space. When we look at different points in space, if we are assuming that, let's say, the sources are in phase, delta phi 0 is 0, then when we look at one point in space, we calculate what delta r is. And we plug it into here, and we get some number for delta phi. And if that number for delta phi is an even multiple of pi, when we stick it in here into the cosine, we're going to divide by 2. An even multiple of pi divided by 2 is going to be some integer multiple of pi. And cosine of an integer multiple of pi is plus 1 or minus 1. So this amplitude is going to be a maximum in terms of its absolute value, at least. So those would be antinode points. Those collections of points along which, for example, delta r is equal to 1 lambda. This delta phi would be 2 pi. All those points for which delta r is equal to a single lambda, those points form an antinodal line. And then there might be a bunch of points, depending on the situation, where delta r is equal to 2 lambda. 2 lambda divided by lambda is 2, times 2 pi is 4 pi. Plugging that into here is going to give you 2 pi. Cosine of 2 pi is a plus 1. And so the amplitude is again maximum. If you have a bunch of points where delta r is, let's say, a half a lambda, half a wavelength, then we have a half wavelength over lambda, that's 1/2, times 2 pi is just pi. And then we have pi over 2 in here then. Cosine of pi over 2 is 0. The amplitude would be 0. Or if we have a delta r that is 3/2 pi, we plug that in here, this will ultimately be 3 pi. 3 pi over 2 is, or 3 pi divided by 2 is 3 pi over 2. Cosine of that is again 0. So anytime delta phi is an even multiple of pi, this amplitude function is as big as it can be in absolute value terms. Anytime delta phi is an odd integer multiple of pi, this amplitude function is 0. And so those are points along those, or the collection of points along which this occurs are called nodes, nodal lines. So let's look at some sort of ways of visualizing that. So this little figure here shows basically what we were talking about. Here we have two sources that are in phase with each other, and we've drawn a few different circles here. Along this line, we have an antinode. Everywhere along this line, the difference in position, the difference in distance from a point to each source is 2 lambda. Plugging 2 lambda in for delta L, we find that the delta phi then is 4 pi. Cosine of 4 pi over 2 is plus 1. Every point along here, we would have a delta r of 3/2 lambda. Every point along this line, delta r would be 3/2 lambda. Plugging in 3/2 lambda for delta r would lead to a 3 pi for the phase difference. 3 pi for the phase difference, plugging that into the cosine function would give us an amplitude of 0. This is where maximums overlap with minimums. You have no motion, there's no wave. The wave is gone. And again, you have an antinodal position here where now the delta r values are equal to lambda. And then another node through here where the delta r values are equal to a half lambda. And finally, you have an antinode through here where the delta r values are equal to 0. So you have a series of nodes and antinodes. And notice that these two points are a distance of 2 lambda apart. So take the distance between the sources, and that gives you the maximum that delta r can be. If they're 2 lambda apart, the maximum that the difference in position can be from a point to those two sources is 2 lambda. In fact, whatever the distance is between the sources, the biggest the difference in R1 and R2 can be is that distance between those sources. So if it happens to be an integral of multiple of lambda, then these points are all going to be antinodal points. And then you'll have a node line, and then an antinode line, and a node line, and an antinode line. And you'll have as many lines as necessary to go from that delta r equals something times lambda all the way down to delta r equals 0. So in this case, we have 1 antinode, 2, and 3 to get us down to 0. And then there's 1 down here, and there's 1 down here as well. So we can kind of have a sense of The farther apart these sources get, the more antinodal lines we can get, and therefore the more nodal lines we can get. The closer we bring them together, the fewer nodal lines we can get, and the fewer antinodal lines we get. And in fact, these things start spreading out. So we can look at that a little more closely. Down here is a little graphic showing a way of kind of coloring these regions of space. If we think about this as a water wave, two sources vibrating up and down right here and here, sending out these ripples, these are your nodal lines, places where the water is at equilibrium. This is an antinode up in this direction, places where the water is going up and down. At this point in time, this region here, the blue region, is a trough, it's a minimum, and the red region is a crest, a maximum. And as these waves propagate outward, these points experience maximums and then minimums, maximums and minimums. In this graph over here, the two sources are out of phase with each other. And so this point above and below, these points above and below now become nodes. The two waves cancel each other out completely, and the water along these lines doesn't move ever. It's just sitting there. Similar to these lines here, we've got nodal lines through here. Okay. And then we can look at this. We can play with this little graphic in Mathematica. You can change this if you like. Right now, I've got it set up as one source is at a position of -2, the other source is at a position of 2 on in the y direction, so they're a distance of 4 apart. And 1 is, or 2 I should say, the wavelength is actually equal to 1. Yeah, the wavelength's equal to 1 in this. So these guys are 4 lambda apart, and they're in phase with each other. So I have an antinode in this direction. You see maximum and minimum variations. I have a node here, an antinode, a node, an antinode, a node, and so on. And right down the middle here, I've got an antinode. So this is the delta R equal 4 lambda, 3 lambda, 2 lambda, 1 lambda, and 0 lambda. And then 1 lambda, 2 lambda, 3 lambda, and 4 lambda again. And similarly to over here. Let's see just what let's see what happens, and it may take a second. If we move these sources closer together, make this a 1, and make this one a 1. Now they're going to be 2 lambda apart. We'll let this run, and it'll take a second to give us a result. Let's see if it comes up here, but watch what happens to the number of nodes, and also, there it is, let me blow it up, and also how spread out they are. So when we look at this, notice that we have fewer nodes. So they're 2 lambda apart, so this is a delta R equal 2 lambda, 1 lambda, 0 lambda, 1 lambda, 2 lambda. These regions have spread out, the nodal lines have spread out. Okay? And if we were to bring these even closer together, you would see these nodal lines spread out even more. So this is going to get us into some topics that we'll cover in the next chapter, called diffraction. One way of creating two sources of waves. Either you can do it thinking about water waves, where you have two things vibrating up and down on the surface of the water, creating this interesting pattern, creating these nodal lines and antinodal lines. Or you can think about using light. And how would you create two sources of light, two sources of identical light? Well, you'd use a laser beam, and you'd send the laser beam through two holes, two narrow openings. Each narrow opening would act like a source. And then the light coming out of those two narrow openings would go off to the right, let's say, and the waves would interfere with each other, and you'd get these regions where you have large variation of light, of the light wave, the electric field, in other words, and you have places where there's nothing. You'd have dark spots and bright spots. And you'll find that when you bring the two openings closer together, the positions of these dark spots, these places where there is no light, these nodal lines, those positions spread out. So there's this sort of reciprocal, opposite kind of behavior of the distance between these nodes and the distance between the sources. As the sources get closer together, the distance between these nodes gets further apart. And we can try that one more time. Make this 0.5 and this 0.5. We don't want to put them right on top of each other, but bring them a little bit closer together. And we'll see how much spread out those nodes get. Give it a second. There we go. Look at that. Beautiful. So look at those two nodes now. They're really spread out. There's a big antinode in the middle and a big antinode up here in a sense. And technically there's variation in the amplitude. Along this direction here is when the amplitude is the maximum. As you move outward in this region, the amplitude gets lower and lower and lower until it finally goes to 0. And then as you come in this direction, the amplitude gets bigger and bigger and bigger until it's a maximum again. And then you come this way and it goes to 0 again, and then goes to a maximum again. So the amplitude is continually varying as you move around these two sources. But the antinodes just refer to places where the amplitude is the largest it can get. The nodes are places where the amplitude is 0. So this covers the majority of what we need to talk about for two-source interference. And we're going to do this more in the next chapter when we talk about light. We'll do this with light, demonstrate it with lasers, and understand some interesting things about diffraction and interference. So until then, have a good afternoon.